So, good afternoon, everybody. I'm delighted to introduce our following next panel speaker, Professor Yury Gogotsi. He is the back endowed professor of material science and engineering at Drexel University, Philadelphia, USA. He is also the director and founder of the Drexel Nanomaterials Institute. Professor Gogotsi's research is centered on the discovery, development, and chemical modification of nanostructured carbides, 2D carbides, and other nanomaterials for energy, water, and biomedical applications. Professor Gogotsi has co-authored 2 books, published over 800 articles, and holds more than 80 patents. His work has been cited over 100,000 times, 4 of which are mine personally, and has an H index of 177. He has received over 40 national and international awards for his pioneering research and has been highly acclaimed by many societies. With that, please welcome to the digital stage, Professor Yury Gogotsi.
Thank you very much, for this kind of introduction. I'm really delighted to speak to you today. I have many good colleagues and friends in Israel, and thank you for this opportunity. I wish I could be at the conference in person, but for more than a year, we have been communicating online, and I'll do my best today to introduce to you this very large, the fastest growing family of 2-dimensional materials, which we call MXenes. And I know there are people in the society who work on different materials in different fields, and you may or may not be familiar with the subject, but I hope after this presentation you will know more and may actually get interest in developing and discovering new materials in the system. You can see some of the structures on the cover slide. They come in a variety of different colors, and they also have a variety of useful properties. And actually, just a couple of weeks ago, we published a review article about those materials with the title exactly following the title of my talk. So if you are interested to read more, this is the latest, most up-to-date review in science here. But let me take a step back and talk about 2-dimensional materials in general here. There is a tremendous interest which was fueled, of course, by a discovery of very interesting physics in graphene by Andrew Geim and Kostya Novoselov. And this actually attracted attention to other 2D materials. And traditional metal, dichalcogenides, and Professor Resheftena, who I see in the audience, is one of the pioneers and world leaders in the field, have actually been studied similar and in parallel to carbon materials. And actually, molybdensulfide was even delaminated before graphene. Boron nitride as a structural to graphene. Clays, oxides, many other materials were known to have layered precursors with weak bonds between the layers that could be delaminated into these sheets here. But what is amazing here, all these materials offer a variety of properties here. If you look at them, they go from metallic to semi-metal, semiconducting to insulators. They have mechanical flexibility because thinner material is always becoming flexible. Bending basically forces inversely proportional thickness power 4, and optical transparent in thin films. And 2D is anything will be transparent in nanometer thickness here. And of course, a large size of the flakes, atomic thickness, allow high surface area for catalysis, for many other applications here. And how I look at these materials is that's really with the variety of materials we have today, more than 2,000 predicted to exist, couple of hundreds experimentally demonstrated, that we really have building blocks for the new world, when we have nanoscale bricks, Lego stones to make components we need. Moreover, let me just jump back to this figure here. What is also important, after exploration of known 2D precursors, researchers started to make materials out of structures, out of basically elements, which were not known to have two-dimensional or layered weakly bonded precursors. Silicene, germanine, boraphin were produced. And actually in 2011, together with my colleague Michelle Barzoum at Drexel University, now a student at the time, Michael Nagib, and several other students, postdocs, and collaborators, we published this article in Advanced Materials, reporting on an entirely new family of two-dimensional materials, carbides and nitrides of transition metals here, which actually, as I'll show you later, added a very large number of, first of all, metallic 2D materials, which were a kind of a missing link with many semiconductors, semi-metals, insulators available in the field. We also got a number of 2D metals and also materials with very interesting properties here. And the initial development was kind of slow because we discovered at the time there were so many other 2D materials known here. But in the last couple of years, development started quickly here. So let me introduce using this slide from an editorial we wrote with my former postdoc and now professor at Purdue, Indiana, Babak Anasuri, in 2019. So MXenes M in these materials stand for a transition metal, one of those blue elements. X in the formula stands for carbon or nitrogen. T stands for surface termination. So on one hand, you can look at these materials as kind of a thickest, bulkiest of two-dimensional materials, but each flake comes in the same thickness. So it's really 2D. Its properties are well defined by composition and structure. And as a result of wet chemical or molten salt synthesis, there are surface terminations on the surface. So in 2019, there were just 4 elements possible: OH, oxygen, fluorine, chlorine here. This is a layer, which actually gives very interesting properties to the material, as I will explain a couple of minutes later here. But just 2 years after that publication, we produced a virtual issue on MXene. ICS-Nano alone published about 150 papers on the subject. Advanced Materials family produced more than 500 papers. And you see, there are many more termination added. There is another even thicker structure with 9 layers of elements and 2 layers of terminations is produced here. So the field started to grow very, very quickly with a couple of thousand papers per year. We had a conference last year at Drexel University. Again, it went virtual because this was a COVID year, but we had more than 2,000 registered participants from 63 countries and more than 750 institutions. So as you see, the field grows. So now we have in this family already a variety of structures. So as I mentioned again, we have layers of transition metals bonded by carbon, nitrogen, or a mix of those. Moreover, we can have this M2X, M3X2, M4X3, M5, X4 structures, and potentially there is no reason why we cannot make even thicker, well-defined structures. And I'm talking not about a single flake grow, and I'm talking about millions and billions of flakes, as we can produce grams and hundreds of grams of the material. Moreover, we can make not only pure material, we can make solid solution where either M elements or X elements will be mixed in a random way. And very recently, actually, the peer papers were published officially after our science review within the last couple of weeks. High entropy multi-elements with 4 equally mixed elements, MXenes, have been reported as well. It's the story doesn't end here. we can make materials with in-plane ordering, where you have alternating atomic columns of elements coming on the surface. And if you actually remove one of them, for example, from moly scandium carbide, you remove scandium, you will end up with materials where you have monatomic vacancies layer, like a vacancies layers going through the structure and making like a ridges on the surface here. Or we can make structure with one element. For example, moly is on the surface, another transition metal in the middle, kind of atomic sandwich structures here. And I'm sure this is not the end. So we basically push it to atomistic engineering of two-dimensional materials. And actually, Professor Tanner demonstrated closed shell structures and nanotubes made of moly disulfide. And MXene nanotubes have been predicted theoretically. No one made them. So this is a potentially one of the targets for future research. Even so, of course, we saw scrolls, again, just like other thin and flexible 2D materials. So it's a very large field. Initially, materials were made from so-known max phases, which Professor Bazoum at Drexel has been developing by removing this A element, one of the marked here glue, basically. So what is important? We do have layered precursors, and there are many others I don't have time to talk about today, layered carbides, moly, to gallium, to see other type of structure, not max phase here. But the key is here that we don't like physically delaminate these materials. We chemically etch monolayer, double layer, triple layers of either other metal or carbide out of the structure. So it's a different method because there are strong bonds in these max phases or other carbides between the layers that need to be removed. And the first one and the most studied one is titanium 332. It's a very nice, actually, 2D material because titanium and carbon are both very common elements here, abundant, inexpensive. And already in the first study by Michael Nagib, a dozen of materials have been produced, also including solid solution on X side, and I showed you many more existing today here. So the synthesis is done typically today either by wet chemical etching of max phase or other precursors, or by emulsion salt etching. So it's a chemical synthesis, which has its, of course, limitations, but also strengths. So after etching, after removing a element or other binding, basically group of elements, we end up with multi-layer structures, which now bonded by weak either van der Waals forces or by hydrogen bonds, and they can be delaminated, intercalated the same way as other materials here. What is important? If you look at the majority of materials, except graphene, boron nitride, moly disulfide, tungsten disulfide, all other these nanomaterials people talk about are produced in extremely small amount. Borofin, which was discovered several years ago and basically announced with big fanfare and studied here, it's still made really as a monolayers supported on a film, on a substrate. And there was a paper in Science recently from Mark Herson's group from Northwestern showing that hydrogen termination can stabilize it. At least it can be taken out to air, but it's again different material now here. And for some application like electronics, it's perfectly fine when we build a monolayer on a substrate. But for many other applications, biomedical, antennas, shielding, printed electronics, catalysis, and of course more for batteries, environmental construction, we need much larger amounts of materials. And the important thing about MXene synthesis, from day one, we could make grams of these materials. Now there are 100-gram reactors in our lab designed for us by a small company in Ukraine manufactured here. There is a 1 kilogram reactor available already in industry, which scales up here. And we can use this material and just simply, for example, Dr. Blay a slurry of MXene and produce films here. So if you look structurally at initial MXen precursors. You see these layers in this example of titanium 3C2. So those are three brightest layers of spots are titanium atoms you can see in the structure. And you can see in between layers aluminum. After etching, we get particles of ceramic looking like basically thermally expanded graphite or vermiculite clay. And you see intermediate layer disappeared by surface termination. This more faint dots appear on the surface. And after delamination, and we can do it by intercalation, for example, or sometimes without, depending on method of synthesis here. We get these sheets, and this is a single layer. In this case, probably like a 6-7 micron size. Here we can make up to 20-30 micron flakes now here. What is important? Because of this surface termination, this material is hydrophilic. So we get a material which is on one hand is a metal. Electrons of this transition metal provide metallic conductivity. So true metals with high density of states at the Fermi level and metallic properties, but they're water soluble without any surfactants. So we can get this slurry colloidal solution, stable colloidal solution in water. Zeta potential is typically below minus 30 millivolts, so they form stable colloidal solution, from which we can either make ink. We can use a highly concentrated slurry to make films directly here. And this is about 50 grams of powder you can see here in a dish here. So we can use basically any solution process technique just for other colloidal solution, nanoparticles, and produce a variety of film structures, aerogel, you name it. Anything you can make, for example, with graphene oxide, you can make with MXene, but it's conducting. Moreover, if we take a highly concentrated solution, it forms liquid crystal. And we can even draw fibers from this liquid crystalline MXene and produce fibers here. One more thing, initially, we observed degradation of materials, not immediate, but within days, weeks in solution. In presence of humidity, water, the flakes would degrade. When they're produced in the film, they're stable for a very long time, at least years. But when you have monolayer flakes in solution, they will degrade. We were able to resolve this issue. We published a paper a couple of months ago in ACS Nano showing that if we get stoichiometric MXene with no vacancies in carbon sublattice or oxygen present here, we can get the material which will, like after 6 months in colloidal solution at room temperature in argon closed vial, will not change at all here. Even after 10 months, we can see only a couple of pinholes appearing after storage. They are circled here because you would not even notice them otherwise here. So they're stable for processing, storage, and shipment before you produce the films here. Let me summarize basically what we have right now. So we have this enormous family of materials with more than 30 stoichiometric structures and probably about 20 solid solutions and multi-element MXenes reported already here. They are water soluble without any additives, binder, anything that can be solved in polar organic solvents and process it in, for example, this type of multi-layer film or use a single flakes here. You can see they look like many other two-dimensional material. If you look at this transmission micrograph, they're single crystals as electron diffraction shows and high resolution TM here. But one thing you may notice, they're much more rigid. So you can have a hanging film over a hole in a grid without support and it will hang. Graphene won't, it's like it is flimsy, collapse here. And reason is this couple of couple of atoms in the structure, much higher rigidity, and also very high mechanical strength. That's why by solution processing, we can make flakes which go up to 20-30 microns, and we cannot make the same with molybdisulfide, for example. It doesn't have sufficient strength here. But as I mentioned, one of the key properties is high metallic electrical conductivity. This is where this material is largely also added to the array of existing materials. And you can see, for example, here, MXene is assembled in a film, several micron thickness. So there are a couple of thousand of flakes in cross-section here. So we have like a metal with a surface like oxide, hydroxide. It can also be halogen terminated material things here. They also come in a variety of colors because of surface plasmons, which cover a wide range here. And also transition metal are electrochemically active. So we have a large electrochemically active surface. So we can use them as catalysts, we can use them for energy storage as application. And electronic properties are tunable, but what is important? We have really ability to design, atomistically design materials. So we can get properties we want. And also there is a big difference, for example, with chalcogenides. We're very limited to the surface being a chalcogen, so we have smaller number of choices. Here, we have a dozen of transition metals, and they are basically oxygen, OH as a bonding source. So we have this very large tunability. We still need to learn how to tune those properties here. How to move from mixed termination to bare uniform terminations here. We can also, of course, put various types of molecules, adsorb or chemically bond to the surface. And by doing this, we can change, for example, work function from 2 electron volts to 6 or even 8 electron volts by going from, say, OH to oxygen terminated surface. It's possible to also, at least by theoretical prediction, open the band gap in materials, but again, changing composition, changing surface termination here. And all this variety of colorful structures, complementing color in MXene come from surface plasmon. So in transmission and in reflection, they will have different colors. For example, titanium 2C will be like a red, pink in transmission and green in reflection. And this may actually remind me of a famous cup from the 4th century, which is used as one of the example of first nanotechnology work here. And of course, you can do this tuning of colors, but it means positions of surface plasmons and other properties even more finely by forming solid solution, but mixing different amount of transition metal, and you will smoothly change positions of plasmon resonance peaks that you can see here. Also, you will see that this plasmon resonance absorption peaks, those surface plasmons, they cover a very wide range of wavelengths. There are electronic transition in the UV range, and then we go from UV to infrared. And they have very high mechanical properties as well, not as high as single layer of materials produced by CVD, because they still have some of the defects, but they are higher than solution processed materials, at least all here. And as I mentioned, all these properties depend on the composition and structure. But if you take certain composition, for example, I already stressed titanium 2C, which has actually color combination, very similar to Lycurgus cup here. And if we have titanium 32 surface plasmon at about 780 nanometer, it shifts down by changing from 3 layers of titanium to 2 layers. It shifts first down towards UV when we replace titanium with vanadium here. So we can make materials which have similar combination of optical properties, but without gold or silver, which were used this here and actually still used widely in plasmonic applications here. And of course, all this variety of diverse structures find already a number of applications. One of the applications where MXene so far showed the absolutely best performance is electromagnetic interference shielding. They're very attractive for printable antennas. We can make antennas which are 10 times thinner and lighter than copper antennas and have pretty much the same performance in 5G, 6G, terahertz frequency range here. Energy storage, battery supercapacitors, filtration, separation membranes, sensors, medical applications. I don't have time to go, of course, in detail today. I want to finish within the next 10 minutes or so here. I will just give you some glimpse of possible applications, and you can just use your imagination and your knowledge and think where and how you can use it in your field potentially. For example, I mentioned that MXene are highly conducting and transparent in thin film. And we were working with Korean collaborators to show that it's possible to place ITO in organic LEDs, and we get pretty much the same performance as ITO, but now the devices are flexible, and all the solution done simply by solution processing. All manufacturing can be done by a compatible process, and it doesn't crack when device is deformed here. We can replace gold or other metal current collectors on flexible transparent substrates with MXenes. It's possible to make gels, hydrogels, aerogels, and you see this is a highly stretchable gel that can be used for strain sensing here. Actuators and sensors, both mechanical, chemical, and electrochemical here. Moreover, with such a variety of properties, some people like Hossam Al-Sharif from KAUST already talk about an emerging field of MXetronics. So electronics that uses MXenes to make complete devices because of such a variety of properties, such a variety of chemistry structures available to control those properties here. In my group, we work a lot on electromagnetic interference shielding and more recently communication antennas that I mentioned here. When we published the first paper on MI shielding in 2016 in Science, showing that titanium-32 pretty much lines up nicely with copper, aluminum, other metals in MI shielding, it was like absolute breakthrough in the field. There was very little progress in the entire field of electromagnetic interference shielding in terms of new materials over years. And we showed that we can have performance like a 10 to 100 times better than graphene. And 1 micron films are sufficient to provide like a 50 decibel, which is the standard for electronics instead of using metal foils. But last year, in another paper in Science, we showed titanium carbonitride MXene with lower conductivity than titanium-32 actually outperform metals, even copper, in absorbing radio waves, electromagnetic waves here. So new physics is involved. I don't have time again to go in details, but it's really different mechanisms that work here. It's not just conductivity and free electrons or magnetisms that was used for make much thicker, usually millimeter thin film. So for flexible wearable electronics, extremely important. The same comes for antennas, when we can print thin antennas for a wide range of applications here. Energy storage. My group has been traditionally working on supercapacitors, battery, other applications. You can look at MXenes, that a material that has electronic conductivity. It's a basically highly conducting. So what it means, for example, high power, high energy battery. High power means you need to run a large current through your device. So you cannot do it using, for example, oxide cathode in lithium-ion battery. This material has electronic conductivity needed, but there are also channels for ion transport between the layers. So it's possible to make materials which will have redox energy storage because of transition metal on the surface, which have very fast electron delivery and ion delivery, making ultra-fast energy storage devices. And again, they can be bulk devices, but they also can be printed on a silicon wafer, as you can see here, or knitted or woven into textiles. Because conductivity changes as a function of intercalated or adsorbed molecules, MXene can be used as a gas sensor. Moreover, metallic, not semiconducting gas sensors here. And there are applications which you would not consider initially for the material, but high surface area leads also to adsorption. And one of the very important problems we're trying to solve now with colleagues from School of Medicine at Drexel, and also a company has been started in the US, spin-off from a Korean company to develop it here, is building a wearable artificial kidney. Millions of people in the world suffer from kidney disease. And actually, you might have read in the literature that after the first wave of COVID, up to 30% of patients who ended up in hospitals here had serious complications with kidney and acute kidney disease because of organ damage, sepsis-like damage produced by COVID here. And the problem with developing wearable kidneys, there is no good sorbent for urea. Activated carbon, which is an excellent sorbent for majority of molecules here, has very low absorption of urea. MXenes appear to be excellent sorbents for urea, but also other uremic toxins. And we showed this in a paper, first paper in 2018. And by now we're working on prototype systems already with industry to create devices, wearable devices that will be able to absorb urea. So you see, potential range of application is extremely wide, just because we have so many different materials with so many different properties here. It goes from energy storage, and this is actually sectors here in this pie chart reflect the number of papers roughly as of about a year ago in the field. So you see about 25% is related to all kinds of battery supercapacitor, pseudocapacitors research, from anodes to cathode, separator, current collectors, and conducting binders, to various types of catalysis, electrocatalysis, hydrogen evolution reactions, nitrogen reduction, and so on here. I talked a little bit about electronic applications here, but of course, everything from triboelectric generators to spintronics is potentially possible. Again, MXene can contain chromium, manganese, other magnetic elements. And people also show, Dmitry Talapin's group at UChicago showed superconductivity in niobium carbide MXene, which is termination dependent, as Boris Jakobson predicted several years ago. I showed you some beautiful plasmonic colors of MXene, but of course applications are in surface enhanced Raman spectroscopy, lasers, and transparent electronics, as well as electrochromic devices, because we can change those colors electrochemically here. Medical applications, photothermal therapy, drug delivery, medical electrodes, replacing silver, gold, platinum electrodes in electromyography, and other basically application for cardiogram, encephalogram, and so on. And here, membranes for separation, where again you can use as graphene oxide, make a hydrophilic membrane, but you can control transport by applying potential because of conductivity of the material here. I talked about shielding antennas, and of course, you can also put MXenes into composite materials, ceramic, polymer, metal matrices, but you can also combine them with non-2D materials, for example, nanotubes, whether those will be carbon or molybdisulfide or others, developing further hybrid materials here. What we believe is very important, they slowly start moving towards commercial production. Millipore Sigma is going to start offering them. There are several small companies that offer materials right now here. And in April this year, a MXene association was formed by Terence Barkan, the same person who created Graphene Association here, to bring together manufacturers and users of MXene here. There are, of course, many, many different challenges in the field. First of all, as you see, with this number of materials, we need hundreds and thousands more researchers. There are already more than 1,000 organizations that published, not people, organizations that have papers just by affiliation, if you look, published in MXene. But so much more needs to be done. For example, CVD-PVD growth, vacuum growth of material is still to be explored. There have been several papers producing very thin layers, for example, like moly to C, but those are not monolayers here. This is Ren and Huimin Chen work from AMR here. Trying to produce MXenes, they actually discovered a new type of two-dimensional carbide, a type of moly, basically metal silicide nitride material. This paper was in Science last summer here. But clearly, CVD-PVD growth is next frontier as well here. And of course, achieving uniform termination, controlling properties through chemistry of these materials, exploring properties of bare MXenes, which will be like electride bonded or monolayers, creating two-dimensional ferromagnets, and many, many other are still the target here, need to be explored. If you want to also learn more about MXenes, we will be offering a course, 5-day course, week-long course from August 2nd to August 6th. And actually it's from 7 a.m. to 12 p.m. Eastern Standard Time. So it's very convenient, starting 2 p.m. In Israel. If you're interested, you can register it by going to our website here. And with this, I'm going to stop. I just want to thank many, many people who performed this research. Of course, all my students, postdocs, visiting scientists. This picture was taken in June. Actually, this was our first like a maskless gathering. We all have been vaccinated by now. In my backyard, getting a summer party here. We'll also collaborate with many people around the world. It's basically list is very far from complete. But we work also with scientists in Israel, for example, Doron Auerbach, Nathaniel Spiegel, and colleagues at Bar-Ilan, Michael Levy, others at Bar-Ilan University. We work on optical properties on optoelectronic application with Alina Karapchevsky and Ben-Gurion University. And this list can be continued. We also have support from BSF for collaboration. And of course, this work would not be possible without funding from a variety of US and international funding agencies and also industry as well here. And with this, thank you very much for your attention. I'll be glad to answer questions.
So, does anybody have any questions? We've got time for numerous single questions.
I have a question. Yury, can you expand a little more on the synthesis side? You mentioned about the CVD of monolayers being a challenge so far, if I understood correctly. And but for the bulk side, can you just expand? You showed one slide at one point that
well, again, I clearly ran very quickly over a large volume of material at the risk of being superficial here. So let me just get back to this slide. So initially we started with material which are known max phases. Basically, those are layered structures where mono layers of carbides and nitrides, like with the structures as MN+1 AXN, are separated by monatomic layer of A element. We typically use material with aluminum or silicon layers here. There are also other similar, which I don't have picture here, carbides. For example, aluminum carbide layers, zirconium carbide layers. So what we do, we take this powder, and this is basically a ceramic. It's produced by ceramic technology, large quantities. You can produce ton of them. For example, Kanthal in Sweden use them as heating element or high temperature protective coating here. We just dump the ceramic powder into solution. Stir for a while. In a reactor that I showed to you, this powder, we end up with a powder in which now there is no more aluminum or silicon or whatever was connecting these layers left. And this is now weakly bonded with OH or oxygen or fluorine on the surface particles here. So if you intercalate, for example, lithium ions or tetraethylammonium, just like you would delaminate molybdensulfide and isosanicate, or sometimes you simply shake the solution, they fall apart into single layers floating in solution because there is negative surface charge, there is repulsion between the layers here. And we get, this is a 1 liter bottle with probably like a 10 milligram per milliliter. It's our kind of a stock solution standard of titanium 332. And from this powder, basically, we go into solution, and from solution, we can do vacuum assisted filtration, we can strain it here. But you can also, instead of HF or in situ HF formation, lithium fluoride, HCl, or similar agents, you can use also emulsion salt, chloride, for example, eutectic salts. And similar way, HA the material, then your surface termination will be, say, chlorine or bromine, not oxygen here. So those are kind of a chemistries involved currently into the synthesis here. But in all cases, we end up with a powder that can be delaminated into single flakes afterwards.
Professor Gogotsi, we have time for 2 more questions at max. So,
I see Professor Tena has a question.
Yeah, can I ask you, Yury, a question about the low temperature physics of these materials? Anything very exciting on the low temperature physics of these materials?
Yes, but let me tell you here. First, I already mentioned very briefly that, say, Boris Jakobsen predicted chemistry-dependent superconductivity on like a moly to C niobium to C. Dmitry Talapin at UChicago, and unfortunately, again, I did not include, I think, any figures on this, showed that niobium to C goes to superconducting state at like a several Kelvin, but only with a certain termination. Actually, it was sulfur, selenium, tellurium, I believe. And if it's oxygen, it won't. And you can also consider, depending on surface termination, you pull different number of electrons from the surface. For example, chlorine will take 1 electron, but oxygen will pull 2 electrons from each layer here. So we get this surface chemistry, and this is actually density of state here showing tunable electronic structure. So we see, we reported recently on antiferromagnetic transition about 35 Kelvin in chromium titanium carbide here. There have been predictions of superconductivity number of materials here. There are effects that we are trying to understand, like hysteresis of conductivity due to surface group or intercalants here. But there are relatively few papers reporting conductivity here. We cannot, for example, explain still magnetic resistance. There are drastically changing and very different negative or positive magnetic resistance depending on composition and structure here. So there are quite a few open questions in the field. So there are more questions, many more questions than answers right now. But this is actually what makes this field exciting, because we already know there are many very useful materials that can be produced by scalable technology, and lots of very interesting science, physics, and chemistry to be discovered and understood and explored with these materials.
Thank you. Anybody has tried to do twistronics with these layers?
Yes, there was a paper published 2 or 3 days ago. Can check, and this is the only work I know. And of course, after graphene and dalchricagenides, everyone is trying here. So they showed, actually, it was, they did not like took in a controlled way and rotated crystals. They simply went to these delaminated flakes and look at basically 2-layer flakes which were randomly assembled, and the ones that were in registry and the ones that were slightly rotated and show different properties. But the paper, as I mentioned, was published earlier this week, I think on Monday. So I still need to read and digest it here. It was in ACS, Applied Materials and Interfaces.
Professor Gogotsi, I'm sorry to interrupt. Where I need to finish. I can leave you in the room if you want to continue discussing it. I will not close the session because it's obvious you have tons of things to discuss.
I would just suggest, since I also unfortunately have to switch to another meeting very soon here. You can go to my website, and both if you're interested in information, papers, we have our publications on our website that you can access here, but also my email. And if you have questions or interested in learning more about MXene, please feel free to contact me, and I promise to answer any requests. We'll also look for PhD students and postdocs. So if you're interested in exploring the field, let me know as well here. And again, thank you very much for your attention. I, in advance, congratulate award winners. And wish you success, and hope to meet many of you in person in the post-COVID, hopefully not so remote future.
Thank you, Yury, for
much.
joining this, and we wish to have you at one of the AVS conferences in person instead of just online. Thank you.
Have a great day. Bye-bye.
Thanks for
Thank you.
the presentation.
Bye.
Bye-bye.